Hi, everyone. Good morning. Well, my name is Fernando. I belong to Sustainable Mobility and Future Department in AIMPLAS. And today I'm going to showcase the forest project, and I would like to introduce you this project and introduce some of the work that we have been doing here about sustainable lightweighting of hybrid pultrudates. As an overview, Forest Project is a European research project which is under the topic of advanced lightweight materials for energy efficient structures. It's funded by the European Union Horizon Research Innovation Program. It started in December of 2022. It ends this year in May. So we are, well, I get the opportunity to tell you that we are having the final event here with some of our colleagues. And I invite you to visit some of the booths, for example, from Bitreds or from Gen2 Carbon, which are around the corner here. You can get more information there. So this project is constituted by 15 partners all around Europe. And the vision and the goal, Forest Project is contributing to the decarbonization of the transport sector by developing innovative bio-based resins and additives and recycled carbon fiber. And the main goal is achieved combining three key drivers: reduce, recovery, and reshape. With Reduce, Forest aims to reduce the structural weight in vehicles by providing light composites fully made with fully recycled carbon fiber reinforced resins. This way, it will lead to less energy consumption in the transport sector. And moreover, we are developing new chemistries based on bio-based resins, which also lead to reduce the fossil fuel dependency. Regarding recovery, Forest is implementing methods to recover 100% of carbon fiber waste in order to obtain high-quality semi-finished materials for valuable applications in the transport sector. And with Reshape, Forest aims to research the influence of multifunctional materials in order to give extra properties, additional properties to these composites, and therefore combine the bio-based, fully recycled carbon fiber and multifunctional materials to obtain sustainable solutions for the mobility sector. As the main objectives are, well, Forest has been developing novel lightweight multifunctional biocomposites for this mobility sector. These new chemistries are based on highly bio-based materials and fully recycled carbon fiber. In addition, as I said, multifunctional particles to add multifunctional properties such as emission shielding or flame retardancy. Hello? Oh. These composites these candidates are obtained using one-shot manufacturing techniques. For example, involving out-of-autoclave manufacturing processes in order to make this processing more sustainable. Forest is important that Forest is addressing sustainability challenges related to the transition towards a circular economy in Europe. And well, the value chain begins with the development of three different resins, two thermoplastic and one thermoset. The first thermoplastic resin is bio-based polyamide 6 developed by BASF. The second resin, thermoplastic resin, is a bioacrylic developed by Arkema with the name of Ilium, probably you know them. And well, they have increased to the maximum this bio content. So the last resin is thermoset. Is developed by Vitrex, and the chemistry is a biobenzoxazine. And all these three resins are combined with functional additives in order to obtain different properties. This multifunctionalization has been performed mainly by AIMPLAS and Clariant. And the first resin, the bio-based polyamide, has been combined, well, has been used for the first demonstrator. This resin has been mixed with fully recycled unidirectional carbon fiber recovered by Gen2Carbon in order to manufacture UD tapes. And then these UD tapes have been used in a thermoplastic pultrusion system to manufacture this profile, flat profile, for the bus roof covering panel demo for Mercedes in Turkey. The second resin, the acrylic resin, has been mixed with, combined with non-woven recycled carbon fiber, also developed by Gen2Carbon, by process of CRTM in order to obtain organosheets, which were afterwards used by Jules Verne in a stamping and overmolding process to obtain the second demonstrator, which is an aerocockpit ceiling part. It's led by Stelia, which is now Airbus Atlantic. And last but not least, the biobenzoxazine was optimized, and SMC or prepregs were developed by Fraunhofer with help of Fraunhofer together with Vitrex using the non-wovens of Gen2Carbon. And these prepregs afterwards are using by compression molding by MBHA to manufacture the auto cover battery pack for Stellantis is the leader of this demonstrator. So in this presentation, I'm going to give you a little overview on the first demonstrator about thermoplastic pultrudates. And here we have an schematic, an overview of the process, the manufacturing process. It all starts with recycled continuous carbon fiber, the biopolyamide 6, and some flame retardant additives, which are mixed together in LFT. It's a long fiber thermoplastic process. With this process, we obtain the thermoplastic UD tapes on one side. So we tested these materials in a pultrusion system, but we obtained preferential orientation, preferential properties in one direction. And for this specific demonstrator, we needed better properties on the transversal direction. So we decided to make a hybrid, incorporating an inner layer, a core layer of non-woven recycled carbon fiber as well. So for this step, we included an additional step of manufacturing a organosheet made with non-woven and biopolyamide film, in this case by a thermolaminated commercial equipment. And then we use these organosheets together with the UD tapes in a thermoplastic pultrusion process to manufacture the flat profile of this hybrid laminate for the bus demo. Just to give you an idea of the UD tape development, we use this. We have here this schematic. Well, basically, it's a long fiber thermoplastic pilot plant, and what we have here is basically a downstream. We have the carbon fiber supply. It's continuous carbon fiber bobbins, and these bobbins feed the impregnation system. It's a melt impregnation system in which we melt the resin together with the additives, in this case the flame retardant. And then with a series of calendars and pullers, it's in the end it's a pultrusion system as well. So we obtain this UD tape. We get these bobbins on the right side. At the bottom you can see some images of the process, and on the right you can see the pristine continuous recycled carbon fiber from Gen 2 carbon. The pellets, the actual resin that we use, just to give you an idea, an image. And then we have the product, which is the UD tape that we will be using for the post-processing with the pultrusion system. On the other side, we have the thermolaminates, the organosheet development. So for these organosheets, what we do is, well, using a commercial thermolaminating equipment in which we sandwich the non-woven carbon fiber between two layers of polyamide 6. Applying pressure and temperature, we obtain this organosheet. It's a pre-consolidated organosheet. So afterwards, we combine these two items, the UD tape on one side and the organosheet. So we lay them up, or we sort them out in a country with a guiding system. So all these tapes and the organosheet is being guided through this system towards the pultrusion mold. This is a pultrusion mold. This is a conventional pultrusion mold which has been adapted to thermoplastic pultrusion, adding a series of heaters. And well, once we process the whole thing, the whole stack, we do the layup and stick it into the mold, and then we, with a pooling system, we obtain the continuous laminate afterwards. Some images of the process. Here's the country with all the bobbins, with the UD tapes, and also the organosheet. All of them are guided with the guiding system that you can see there. And then we can see the dye of the mold, how the profile comes out of the mold. We don't have an image of the pooling system, but well, you can imagine that it's everything is pulling from that profile from the other side. And then we have an image of what section of the Pultruded that we can obtain, although this can be continuously produced. Some adaptations, some modifications of the process. The first one, since we noted that there is a relatively rough surface in this profile, in this laminate, we decided to add a calendar system at the die of the mold in order to add some more compression and try to make a smoother surface in the laminate. We achieved some, but it's still having not the best aspect, since we are using, well, it can be some irregularities, and we might need to maybe improve this part. The second image shows the demonstrator manufacturing, so you see the continuous thread, the continuous manufacturing of the or extraction of the laminate. And then if we wanted to reach a better, smoother surface, we can post-process this in the thermolaminating equipment that I mentioned before. So we can obtain, well, this is in the end the profile, but you see that the surface is quite smoother and better looking in the end. And as conclusions regarding the polymer, we know that the polyamide 6 viscosity is a critical parameter for this process. So to ensure proper fiber impregnation and the strong fiber matrix interface, the thermoplastic has to be very liquid, not very viscous, because otherwise with this method we cannot impregnate properly the fibers. So this is a critical parameter. Thankfully, BASF has developed like low viscosity polyamides, polyamide 6, which is quite tricky. But we achieve enough viscosity, a really nice viscosity for that. Regarding the additives, the use of flame retardant additives must be carefully limited. Since we increase the amount of flame retardants, in the end, this is a load. This is an additive that increases the viscosity of the whole system. So if we increase the viscosity, we have the first problem, which is that we cannot impregnate the fibers properly. We lose this impregnation facility, let's say. So we have to limit the amount of additive that we add, the flame retardant. although we reach levels of flame retardant that improve quite a lot the fire performance of these composites. Regarding the fibers, using non-woven recycled carbon fiber is limited in thermoplastic pultrusion, and I tell you why, because yeah, the non-woven doesn't have a preferential direction, so when you stick it in a mold with high pressure and temperature, if there is not a proper flow inside, the non-woven doesn't want to be pulled in one direction. So what we did here is just lowering the ratio of non-woven, adding more thermoplastic, so there is more fluid inside of the mold to make the whole system flow. So we have to limit the amount of non-woven. We did several trials. If we try to increase the ratio of non-woven in the composite, we have these problems. We have some discontinuities. Sometimes it tears apart inside of the mold. So it's something that cannot be controlled. So non-woven is not made for pultrusion. We achieved some laminates limiting this the good ratio between fibers and non-woven and thermoplastic. But it's something that we have to take into account. And regarding the process, a hybrid thermoplastic pultrusion process has been validated, which is great. Probably the concept or the profile that we're using is a flat profile. Is not the most, you could say, is not the most appropriate for a profile, for a pultruded profile, because you're looking for different geometries. But it has been validated. It has been well. We have demonstrated the technology, and we are sure, and we know that selecting other profile section geometries might have promising results using this technology. And this is all from my side. So thanks to everyone for attending. If you have any further questions, I will be happy to attend. Thank you very much.
Thank you, Fernando, very much. Does anybody have any questions? Perfect.
Thank you very much. One question to Gen 2 carbon. The RCF tape, how is it made?
The UD tape, you mean?
Yeah.
How it's made?
Yeah.
Well, it's a melt impregnation system. So what we do is melt the polymer with a twin extruder. We do the mixing with the additives that we need in the same extruder, and then we have an impregnation bath. So the fibers go through this bath. It has a specific system. So the melt polymer comes into the bath, and in a series there is a series of steps, and then it gets impregnated. And then from the other side it comes out, and we have a puller system. So it's like a sort of pultrusion system in the end, like a miniature pultrusion system. Yeah.
But could you also say how the alignment of the fibers was arranged before that?
How the alignment? You mean the
fiber alignment? Yeah.
From the recycled continuous carbon fiber. Yeah, it's a bit tricky. In this case, it was quite similar to commercial virgin carbon fiber.
Ah, okay.
Yeah, because what they do, you would ask why? How do they produce this recycled carbon fiber continuously? No?
Yeah.
So what they did in this case is experimental part. So it's very tricky because if you have fabrics of carbon fiber, you have to shred everything, and you have short fiber in the end. So what they did for this specific continuous carbon fiber is recycling hydrogen or high pressure vessels, which have been manufactured by filament winding. So what they do pyrolysis of this, and they unwind it.
Okay.
Yeah.
Great.
So the quality of the fiber, obviously, it's I mean, it doesn't have any sizing. It might have some little scrap from the process, but in the end, it's quite good, and the mechanical property is very similar to virgin carbon fiber. So
thank you. Yeah.
No problem.